Hello, welcome to the 5.10 notes. Today we are going to be talking about intro to optimization problems. We're going to just kind of introduce the idea like the word intro means. We're not going to do super complicated problems today, but these problems can be easy and they can get really hard really quickly. And so optimization is the process of making something the best it can possibly be given certain constraints. It involves maximizing or minimizing a certain value or quantity. Examples: minimizing the amount of material needed to create a product, maximizing the profit of a company. And so if you've ever been wondering, how is what we're learning going to connect to the real world, this is it. So we are going to use the first derivative, you know how we use the first derivative to find the max or min. We're going to use the first derivative to find max and mins of these problems to be able to maximize or minimize the things in these problems. So, not always, but optimization problems, generally, if you follow these steps, you can be successful. So first, you're going to read through the problem and don't skim it. Like, really read it. You want to make sure you understand exactly what you got yourself into before you start doing the problem. Then you're going to write the equation of the thing that you're trying to maximize or minimize. And then you're going to write the equation that represents the thing that is constraining you. And then you're going to use systems of equations. I don't know if the last time you touched systems of equations was in Algebra 1. I'm sure you've touched on it a little bit the last couple of years, but we're going to basically combine the constraint and the maximizing and minimizing equation, and then we'll find the critical values. Remember, that's the derivative, and then we'll determine our absolute extrema, so the absolute highest thing that it could be. So we shall get started. This first problem says we need to enclose a rectangular field with a fence. We have 500 feet of fencing material, and a building is on one side of our field, so we don't need any fencing for that side. Determine the dimensions of the field that will enclose the largest area. So I'm going to go ahead and I'm going to draw a picture. So I am told that I have this rectangular field. We'll color it in green. And I'm told that on one side there's a building. Pretend that's a building. It's a very ugly building. I don't know what I was going for there, but building. Okay. And so we want to do a fence, but we only need to do the fence around these three corners because the building blocks off the field from there. And then the big thing I want us to take our eyes to is the word largest. So because it says largest area, you can automatically know that this is a maximizing problem. We're trying to figure out how can we maximize our area. And so that's what I'm going to start off with is I'm going to write my maximizing equation. So the area is what I'm trying to maximize, and you find the area by doing length times width. And so this is the thing I'm trying to maximize. I'm trying to figure out what length and what width would make this field the largest, right? Like, we're trying to make the field as large as it possibly can with the dimension, with like the materials we have. So then that brings me into the constraint. I only have 50 feet of fencing material. So basically, real quick, this is going to be our length, width times length, right? But I only have so much material, so I'm going to have to use my material to do the fence on all these three sides. So I want to make this as large as possible, but I only have so much material. And so to write the constraint equation, it's going to be, so this side I need material for, this one and this one, because it's a rectangle, these two sides are equivalent to each other. So I'm basically trying to make a fence, and I'm using 2L, because this side and this side, plus W, and I only have 500 feet of fencing material. So this is my constraint equation. This is why I can't just make my area as big as I possibly want, because I'm limited by how much supplies I have. And so those are basically, like, I'm understanding the problem. I have my equations. Now I want to try to combine a constraint of 500 into the equation that I'm trying to maximize. And so I'm going to use a system of equations to do this. And a big idea that you might know here is that you can only solve an equation if you have one variable. And right now, if I were to try to do anything, I have multiple variables. And this isn't like a related rates problem where things are changing with respect to time. They're just like variables. And so what I'm going to do is I'm going to solve my systems of equation. And you're always going to want your final equation to have the thing that you're going to maximize. So basically, I'm going to take this equation and put it inside this equation. Not the other way around, because I'm maximizing the area. So I need the area to always be represented. And so what I'm going to do is I'm going to solve this equation for one of these two variables. And because W is already by itself, I'm going to go ahead and solve for W. So all I have to do do to solve for W is subtract 2L on both sides, and I'll get W equals 500 minus 2L. Then I can go ahead and take my area equation, and to get this area equation down to one variable and to use our constraint equation in that equation, I'm going to replace W with 500 minus 2L. And so this is the equation that I'm going to have to use. So this is the equation that incorporates the thing I'm trying to maximize and our constraint right here. And before, you have to take a derivative here because the first derivative is where you find a max or min, or it's where you can like algebraically figure out where there's a max or min. But I'm just going to clean this up real quick. I'm going to distribute because it will help me when I take the derivative. So I'll have 500L minus 2L squared. So this is my big equation right here. But now what I'm going to do is, like I said, the first derivative helps us figure out algebraically where there is a max or a min. So what I'm going to do is I'm going to take the first derivative. A prime equals 500 minus 4L. And then I'm going to set that equal to, hold on, I think I might have done, oh no, we good. Okay, so now I'm going to set this equal to 0. I'll get 4L equals 500, and then L therefore equals 125. And so that is what my length will equal. But it says the dimensions. The final answer says determine the dimension. So I know that my length is going to equal 125. And then my width is going to equal 500 minus 2L. It would be, so I'm just using this equation right here. So I'll do 500 minus 2 times 125. So 500 minus 250. So the width will be 250. So my final answer is the width will be 125, or sorry, the length will be 125 and the width will be 250. One other thing to consider in this one, because we only had one critical point that came out, we didn't have to test this, but it is nice to actually do a line test because sometimes you'll get more than one option when you find the place where there could be a max or min. And like, for example, I want to maximize this area, but maybe there's more than one option. I want the one that actually maximizes it, the exact highest one. But so what I could have done here just to like guarantee I had the right answer is I would do a line test. If I plug 125 into that equation, I would have gotten a negative number. If I would have plugged 126 into this equation right here, it would have come out as negative. If I plugged in 124, it would have come out as positive. So I know that this is actually a max that's happening in there, not a minimum. So that's more important to do though when you have more than one critical point that comes out. So we're gonna do our next one. This one's a little trickier, but should be fine. So this one says we want to construct a box. Sorry, some of the numbers got canceled out here too. We want to construct a box whose base is a square and that has a volume of 36 feet cubed. The material used to build the top and the bottom cost 8 feet squared, and the material used to build the sides is 6 feet squared. Determine the dimensions that will minimize the cost of the box. So basically we have this box. And it says the base is a square. So that means that these two sides are the same. If it's a square, then that means all the sides on the bottom of the box are the same. But it doesn't say that the height is the same. So I'm just going to write H there. And I'm going to go ahead. So that's like all I really know about the problem. It also tells me that the materials to make the top and the bottom are $8, and the materials to make the sides are H dollars. So I'm just going to kind of color these just to remind myself that these are going to be different values. I'm going to start by writing down the thing that I'm trying to maximize or minimize. So it actually uses the word minimize, so that's helpful. So I'm trying to minimize here, and I am minimizing the cost of the box. So I'm going to write an equation to represent the cost. So let's start with the sides, or the top. So the top and the bottom, those are going to cost $8 per foot squared. And so basically you would have to find the area of the top and the bottom and multiply it by 2. So the area of the top and the bottom are both x squared, because x times x would tell you that area, but then there's the top and the bottom. So the area of those two sections is going to be 2x squared, because each one is x squared. Multiply that by 2, and then I multiply that area by 8 to figure out the price of the top and the bottom. Then if you were to find the price of the sides, each side is represented by x, which is the one of the base sides and height. And then there's 4 of those. So it'd be 4xh, and then I'm going to multiply that by 6 because that's what the materials cost per foot squared on the sides. So this is my cost equation, and this is what I'm trying to minimize. Now I want to write the equation of the thing constraining us. And that said, that thing is that it has to be, the volume has to be 36 feet cubed. So the volume equation is side, or like base times height times the height, like, sorry, what am I saying? It's basically side times side times side. It's like the base times the height. So in this case, the volume, which is 36, is going to be x squared times h. And so this is our constraint. And so somehow we need to combine these two equations. We have to include our constraint equation here. And so I have to get it down to one variable. And as I look at this constraint equation, the variable that would be easier to solve for is h because it's not squared. So I'm going to start by solving for that. Oops. So I'm just going to divide x squared on both sides, and I get that h is 36x squared. And so now I'm going to take my cost equation and I'm going to replace x or h with x squared. And as I go, I'm going to simplify a little bit because 2 times 8 is 16. So I'll have 16x squared, and then 4 times 6 is 24. And then I'm going to replace, when I get to h, I'm replacing that with 36 over x squared. And again, I'm going to go one more step before I move on to anything else. And I'm going to simplify. So 24 times 36 is 864. And then x divided by x squared will just make it 864 over x. So this is the equation of the cost, including the constraint that the volume has to be 36 feet cubed. And so to figure out where we could possibly minimize it, we need to take the derivative and find the absolute minimum. So to take the derivative of this, I'll get c prime equals 32x. If you were to rewrite 864 divided by x, that's 864 x to the negative 1 power. So when I take the derivative, it'll be negative 1 times 864 x to the negative 2 power. And if I simplify this up, I'll get 32x minus 864 all over x squared. So this is the derivative equation, and the derivative equation is what I use to find the minimum cost. So I first have to start by finding the critical points. So I'm going to come over here and I'm going to set this equation equal to 0 because the critical points are where it equals 0. I'm going to add 864 divided by x squared on both sides to make it positive. I need to get this x squared off the denominator, so I'm going to multiply both sides by x squared. I'll get 864 equals 32x cubed. And now now that I have the x's together, I have to get x alone. So I'll divide both sides by 32. That equals 27. So I get 27 equals x cubed. So x equals 3. So that's my critical point. That is one place where the derivative equals 0. And so let's check and make sure that's a minimum value. So I'm going to use my line test. If I were to plug in, let's say, 4 into this equation right here, I would have 32 times 4. We can go ahead and think about it. 32 times 4 is 128. 864 divided by 16 is 54, so this will be positive. And then let's say we plugged in 2, that would be 64, and then 2 squared is 4. 864 divided by 4, definitely 64. This becomes 216, so that'll be negative. So there is a minimum at 3. And so the x value that will minimize the cost of our box is 3, but it asks for the dimension. So I also need to figure out what the height is. And I'm just going to go back to this equation right here to figure that out. I know that x equals 3. 36 divided by 9 is 4. And so the height would be 4. And that would be your answer right there. One more problem. Example 3, I think I have to add something. So it says a rectangle is formed in quadrant 1 with one corner at the origin and the other corner on the line y equals 8 minus 2x. Find the largest possible area of the rectangle given its boundaries. So we have a rectangle. I'm going to highlight that. It's formed in quadrant 1. We'll talk about that in a second. Corner's at the origin and the other corner is on this line. we're trying to find the largest possible area. So that means that this is the thing we're maximizing. We're trying to maximize the area. Okay, so let's go ahead and draw a picture. So it says a rectangle is formed in quadrant 1, and what it's talking about is it's talking about quadrant 1 of a coordinate plane. So basically, there's this rectangle that's formed, and it has a corner at the origin. This is the origin, and then the other corner is on this line, y equals 8 minus 2x. So we should probably graph that. This is in y equals mx plus b form, but b is first, so the y-intercept's at 8. So I'm just going to do like a little sketch. If the y-intercept's at 8, it's right here, and then essentially we're going down 2 over 1, down 2 over 1. So it'll look kind of like this. And it says that there is a rectangle who has one corner on the origin and another corner on this line. So it's going to look a little bit like this. This is our rectangle. And we're trying to find the largest possible area of this rectangle. So let's go ahead and start with the area formula. The area formula is length times width, but I'm going to use x and y here because we're working on a coordinate plane. So x times y. This is going to be x, this is going to be y. And this is what we're trying to maximize. Our constraint is actually already given to us. Our constraint is that this corner lies on this line right here. So we know that y has to be 8 minus 2x, because whatever x is, right, whatever this length x is, if you plug in x to the equation, you'll figure out what y is. And so we actually already know our constraint, which is kind of nice for this one. And so now I'm going to combine these two equations, and I'm going to take my constraint equation and plug it in for y. So I'll get a equals, and y was already solved for in this one, so that was really nice. 8 minus 2x. I'm going to distribute real quick to make it easier for us to find the derivative. And this is my equation right here, maximized because of the a, and then the constraint was put in as well. So now I want to figure out the total max area, so I'm going to take the derivative. I'll get 8 minus 4x, set that equal to 0. This comes out to be x equals 2. I'm going to test it out real quick and make sure that is actually a maximum. So I plug in, like, say, a positive 3. That will go negative. If I plug in a 2, or sorry, if I plug in like a 1, that will go positive. So that is a max value. And so then this is the final answer says find the largest possible area. So I actually have to find the area here. But I now know that the x value is 2. I'm going to go back to this equation to find the y value. 8 minus 2 times 2 is 4. So the y value is 4. Therefore, the area is going to be 2 times 4. So the area equals 8. It didn't tell us which units to use, and so it should be 8. Wait, hold on, let me make sure I did everything correct. Yeah, 8 units squared. And that should be it. So let me know if you have any questions, but that's it for the notes today.